Okay, welcome back. Let's get started with Landshark, another example of simulation. So Landshark is a real estate company that purchases properties that it develops and then resells. Landshark has successfully acquired property via first price sealed bid auctions. In a first price sealed bid auction, each bidder submits a single concealed bid. The bids are then compared, and the party with the highest bid wins the property and pays the bid amount. So in this particular problem, Landshark has identified a commercial property of interest, and it estimates the value of this property to be $1,389,000. Landshark has bid data on 13 recent auctions and that it believes are similar to the upcoming property auction. So Landshark is considering a bid of $1,229,000 and would like to evaluate its chances of winning the upcoming bid with this or auction with this bid. So let's go ahead and take a look at our static spreadsheet model. So here we have the static model. This is the estimated value. And in this particular evaluation, Landshark has put in 4 bidders manually. It's hard-coded. And these are the percentage of the estimated value that each bid is expected to generate. So in other words, we take this 1,389,000, multiply it by 0.887, and the bid is for that particular bid number is going to be 1,232,000. Now that it's up to 8 bidders, but there's no guarantee that all 8 of the property development companies will bid on this property. But if they do this, it has hard-coded in percentages of estimated values. And then down here is the model. So these are the parameters. And then our model is, okay, this is our bid amount. This is the largest of all the bids from our competitors. And so it's a max of these values. And we get the largest of 1,200,000. Did Landshark win the auction? Well, if B18, its bid, is greater than B19, its largest competitor bid, then a 1 goes in there indicating it won. Otherwise, a 0 goes in there indicating it lost. And then here's the return. It's B20, did Landshark win the auction, times the difference in the value of the property and what Landshark bid. The other thing to note is our bid amount. What we're doing here is if we have a number greater, if we are at a bid number greater than the number of bidders, we will not put a value in. We put a 0 in that case. So 4 is not greater than 4. So we go to the third parameter, we're for the false branch, and we go ahead and we calculate a value. In other words, we take the bid price and multiply it by the the percentage bid we expect. Down here, 5 is greater than 4, so we just put zeros in there down. Now, obviously, there's some real problems with this. These are all hard-coded values. The number of bidders is a hard-coded value. So a lot of subjectivity there. Now, we do have historical information on bids. right here. So we can use that in our calculations. And then we also have, here's historical information on bidding as well for auctions. So we have a bid list with a bid number and amount, and we've got auction history. So perhaps we can use those to help with what's going on. Well, the first thing we have to do is identify the input parameters for the upcoming auction. One of those is the estimated value of the property. The second is the number of bidders. And then the third is the bid amounts. And as I mentioned, there can be up to 8, but it depends on the number of bidders. So we have those parameters entered into our worksheet. The output that we're interested in is whether Landshark wins the simulated auction. Given its specified amount, it's going to bid $1,230,000. If Landshark wins the auction, its return is computed as the difference between the estimated value of the property and its bid amount. If Landshark does not win the auction, its return is 0. So whether Landshark wins the simulated auction can be determined by comparing Landshark's bid to the largest competitor bid. So again, we look at the bid list and we can determine that the number of submitted bids is going to range from 2 to 8. To determine the largest competitor bid, the spreadsheet model must be able to compute the maximum bid from a varying number of bids. So cell B4 contains the estimated value of the property. Cell B5, a value for the number of bidders. That should be a random value. Cells B8 through B15 contain 8 possible competing bids expressed as fractions of the property's estimated value. And then cells C8 through C15 express the respective bid fractions as dollar amounts using the if function that we went over. So if a bid exceeds the realized number of bidders in the cell, the corresponding bid amount in the cell is set to 0. Otherwise, the bid amount is computed. So let's think about this one and what we want to do. So as I mentioned, one of the problems we have is that pardon me, one of the problems we have is that we don't have random distributions in for the variables with uncertainty. We have statically hard-coded values into our spreadsheet. So in the Landshark simulation model, again, we're going to run a number of simulated trials, but there are uncertain quantities. The number of competing bids is uncertain, and how much the competitors will bid, the percentage of the property's value, that's uncertain. So to specify probability distributions for uncertain quantities, or in other words, random variables, we would first look at the number of bidders, and we have a frequency distribution that we saw in our model, and it's ranged from 2 to 8 over the past 56 auctions. So what has been found is the likelihood for different values for the number of bidders appears to be equal. So Landshark decides to use a uniform distribution in which the number of bidders is equally likely to be 2, 3, 4, 5, 6, or 7. To generate a value for the random variable characterized by a uniform distribution, we saw that we can use the rand function, or there's another one, the rand between function, and that'll generate a number within the range we specify. Now, again, for Landshark, the lower integer value is going to be 2 and the upper is going to be 8. Well, let's take a look at that. So now we have entered randomness into our spreadsheet. And I've clicked on the number of bidders cell, and you can see we're using rand between, a little bit more convenient when we're going to just pick a uniform distribution between a range of numbers. So we're going to do a rand between 2 and 8. And every time we click the calculate now, that will be recalculated. It's at 5. Now it's at 2. Now it's still at 2. Now it's at 4. Now it's at 8. So you can see it changes as we change, as we click calculate now on our spreadsheet. We've entered a randomness in it, and it's equally likely to be between any number 2 through 8, any integer between 2 and 8. Now the other random variable we hard coded last time was the percentage of estimated value. So each competitor's bid fraction is also a random variable. So from the past 56 auctions, there's a total of 280 observations of how competitors have bid. And we find that this is going to be a histogram of basically a discrete probability distribution. And so we will do this. We've got a bid list worksheet. And in the bid list, let's go to that. Let's go up top. We have the bid number and the amount. So we will randomly pick a number in there. So we're going to go random between 1 and 250. That's the number we have in our list. The table is going to be in a separate worksheet, and it's going to be what we just looked at, A2 through B251. We're going to return as a value the percentage, which is the second column. And in this case, we want an exact match. So here's the values, for the bid amount for each particular bid that we looked at. And this is in column 2 that we're going to be returning it, and we want an exact match this time. So that's what we put in here. VLOOKUP, random between, we're going to pick one of the numbers between 1 and 250 from this table and return the percentage value. And then once we've got that, then we can determine, based on the number of bidders, how far down the list of 1 to 8 bidders we should actually calculate things. So there's, of course, several ways to use the 280 or so bid amount observations as a basis for simulating bid amount values. We could use it as a discrete probability distribution, and such a distribution is going to be fairly efficient. Another alternative is to directly sample from the 280 observations to generate values for simulation trials. And the third is to fit a continuous probability distribution on those 280 observations. So direct sampling from data is a good modeling choice if Landshark believes these 280 bid fractions are an accurate representation. So to simulate bids for the upcoming auction, the way we showed and the way, of course, Landshark decided to do it is to randomly select a value from one of the existing 280 historical values. So to execute the simulation trials, what we do, let's go back here. What we do is we have our 1,000 simulations that we put in, and then we highlight our table. And of course, in this case, the number of bidders we get from B5, bid 1 is in our model, that's C8, C9 is bid 2, C10 is bid 3, C11 is bid 4, and so on. So we just take these and put them along here. Winning is going to be B20, and the return we get in a simulation is going to be B21. So now we've got what we're interested in terms of calculating how much Landshark will get as a return in a particular trial. So let's generate 1,000 trials in our simulation. So I'll highlight our model that's here horizontally, do Control-Shift down arrow. Then I'll go to data, what if analysis, data table. And now I get a number of bids, and they will have varying numbers of bidders and varying percentages each bidder is going to make of the overall total. From that, I can look at the average, the percentage of the time or probability that Landshark will win the bid. So I come over to my win column here, which is K, and I just do an average on K25 to K104. We have zeros and ones. Ones mean we win and zeros otherwise. So we just take an average of that, and we're going to get about a quarter of the time Landshark's going to win with that bid. The maximum return they're going to make is going to be the maximum in the return column L. The minimum is going to be the min function applied to that return column L. And then the average return will be an average of that in column L. And of course, we can do a frequency bid. We're only going to get 2 brackets that actually have any numbers, 0 and 160. And of course, we can do a histogram of that and make a chart as well. So that is the Landshark simulation model. Let's take a look at another one. Okay, this is the Press-Teague quarterly exchange rate. So let's take a look at that one. So Press-Teague worldwide manufactures all its products in the United States, but it sells them in 3 different overseas markets: United Kingdom, New Zealand, and Japan. Each of these overseas markets generates revenue in a different currency: pound sterling, New Zealand dollars, and yen. At the end of a 13-week quarter, Prestige converts the revenue from these 3 overseas markets back into US dollars. And that exposes Prestige to exchange rate risk. So to assess the degree of Prestige's exposure, they've developed a simulation model. Let's take a look at that. So the first step is to identify the parameters and then the output measures. The next step is to develop a spreadsheet model that computes the values of the output measures given the values of the input parameters. And then prepare the spreadsheet model for simulation analysis by replacing the static values of the input parameters that are uncertain with the probability distributions that we would expect. So we see that in our worksheet right here. We start with the start of quarter exchange rate, hard-coded value there. Then a change, of course, the start of quarter we're going to know with a high degree of certainty. But how much it's going to change, the percentage change over the quarter, is another matter. That's an uncertain thing, but notice we've got it statically coded here in our model. So then we do the multiplication and come up with the end of quarter rate. And then we have certain quarterly revenue for that particular country. And we then do the division and come up with our US dollar equivalent in terms of revenue. So this is the simple static model. And the problems we see in it already are that we are dealing with hard-coded values for things that we aren't certain of, where we should have instead probability distributions. So, but we always start with just preparing our hard-coded model. Then we identify the parameters that are uncertain, and we replace the hard-coded value with a probability distribution, randomness. So let's look at it again. Once the end of quarter exchange rates are known, the quarterly revenue in pounds, dollar, New Zealand dollars, and Japanese yen can be converted into US dollars. So we do have data. And from that data, we have a history of the various exchange rate changes. So let's go back up top. And so we have the US dollar pound, US dollar New Zealand dollar, and US dollar yen exchange rate changes by quarter for a large number of quarters. So what we can do in our model is a VLOOKUP for the percentage quarterly change. So let's take a look. So now, instead of a hard-coded quarterly change, I do a VLOOKUP, and I'm going to just select a random number, and I have a random number generator that is down in this one. So we've got a random number between 1 and 900. That's in B14. So up here, I take the random number I've generated, I look it up in this data worksheet, and then the table is A2 through D209, and I return the second column, which is the percentage. This is a history table. And I do false. In other words, false means I want an exact match. So here I get my percentage changes. So the start of quarter, we know. The percentage it's going to change over the coming quarter, we don't. But I've calculated those randomly. Now I can do the end of quarter rate because I know with my simulation what the quarterly change is. And of course, this will change every time I hit Formula Now. And then I take my quarterly revenue and divide it by the exchange rate to get my revenue per country and add those up to get my total revenue. So I can make a model. So I'll just clean this out here in the same manner we've done before. I first create a list of 1,000 numbers for my simulation. I put my formula that I'm interested in, which is going to be the total revenue I'm getting. And that in turn is dependent on these random values I generate for the quarterly exchange rate, as I just explained. So I'm going to highlight my trials and my revenue, do control arrow, control shift down arrow, go do my what if analysis. And here, Excel randomly change, well, what it does is it does a calculate now 1,000 times. And you see I get a variety of different total revenues. And I can come over and look at my bin columns for total revenue, get the frequency counts for those, and come up with a chart as before. So again, we've made use of the VLOOKUP table quite often. Okay, so any questions on Monte Carlo simulations? Okay, let's continue on. So we want to make sure that we are giving some valid and accurate results. And there's a process called V&V, verification and validation. A verification is the process of determining that the computer procedure is logically correct. Validation is the process of ensuring that the simulation model provides an accurate representation of the real system. So verification, we rely on Microsoft to have properly tested the various functions that we're using in Excel. Validation requires an agreement among the analysts and managers that the logic and assumptions used in the design of our model are accurate. Then the analyst has to check their work, taking that model and putting it into a spreadsheet. So the analyst is going to review the simulation output to determine whether it's reasonable approximation. And you have to do this verification and validation in any simulation study. So some of the advantages of using simulation is that it's easy to understand and can be done quite easily in both computer languages like R or Python, as well as in tools like SPSS and, as we've seen, Excel. Simulation models are flexible, and you can change assumptions and see what impact they're going to have. So you got to be conscious, though, of the assumptions that go into your model. So if you have a sufficiently large set of trial runs under a wide variety of conditions, you're likely to have sufficient data to predict how the real world's going to operate. Okay, let's do problem 11-1. It's at the end of chapter 11 in the text. And the data set for that is Galaxy. So let's take 10 minutes to do that, and then we'll go over the answer. Okay, welcome back. Let's get looking at this. I'll switch over to the worksheet. So let's take a look at our model. So in this problem, management has done an analysis of the context and determined that a normal distribution applies to the random variable, which is demand for their product. And in other words, demand is going to take on a normal distribution. And as you recall from the midterm, the two parameters that fix a normal distribution are mean and standard deviation. So we've put those in a table in our worksheet. If we examine this worksheet, we see that we have our model set up with the parameters and the model itself. So knowing average demand and the standard deviation for demand, we can calculate the various demand that we would get, and we can use random numbers to come up with a variety of different trials in our simulation. So the first step is to create a distribution of our random variable, which is demand for Galaxy routers. Now the other parameters, wholesale price is fixed with certainty, retail price is fixed with certainty, the amount of profit they make is fixed with certainty, the holding cost they have is fixed with certainty, and the shortage cost is fixed with certainty. It's only demand that is random, and we can see we're using a normal distribution for that. So one of the important things we need to do is to create a distribution of our random variable, demand for the Galaxy routers. And we'll use a simulation of 1,000 trials where we pick different demands from our distribution, a normal distribution with an average of 100 and a standard deviation of 20. So in Excel, we do this by placing our goal in the first row of the table of the two forms, net profit and unmet demand. And so in our simulation table down here, we've done that. We've put the unmet demand, of course, the formulas for those are up here, and we're using if statements and mins and maxes and so on. But these are just standard accounting. Down here is where we're going to generate our trials. So unmet demand is equal to B15, unmet demand in our model. Net profit is going to equal to B18. Both of them are dependent on our demand, our overall demand. So every time we run this, we'll get a different set of values for our 1,000 trials. And of course, when we run it the first time, we'll get a whole set of different ones for each trial. We'll get a different demand, and then we'll get different other variables resulting from different demand from each trial. So let's go ahead, select our trial, unmet demand, and net profit, do control arrow, control shift down arrow, go to data table. For our input, we'll do that. And now we've got a variety of different demand values and also net profits and unmet demand from that. Now we can also then do a minimum on our profit column to figure out what our minimum profit is. We can do a maximum and figure out what our maximum profit is. Look at our average profit in that column of simulations, and then look at the standard deviation. We can also find out what probability or what percentage of the time we have unmet demand. And then we can do a frequency distribution and a histogram as well. And then we can do things like prepare a confidence interval that 95% of the time our average profit will be between, in this case, 4306 and 4463. And then a confidence interval at 95% level of unmet demand between 97 and 99 basically percent. So a fairly straightforward application of what we have done in the class so far. So any questions on this? Okay, let's go ahead, get in your groups and start looking at the group project, start brainstorming on how you're going to divide the work. And we're going to have presentations 4 weeks from now. So we will have class time that you can devote. I'll be walking around, ask me questions as you start reading through the materials. All right, let's go to that.